Hey everyone, welcome back, and thank you for joining us again in our next discussion of statistics. Heading into our objective then, we want to be able to distinguish between independent and dependent sampling. Well, independent sampling is when the individuals selected for one sample do not dictate which individuals are to be in a second sample. While dependent sampling would be when the individuals selected to be in one sample are used to determine the individuals to be in the second sample. Dependent samples are often referred to as matched pairs samples, where pairs of data are matched together for comparison based on some characteristic. Note that it is possible for an individual to be matched against him or herself, but we'll elaborate more with our sampling through some examples. Heading into our first example then, we're asked for each of the following determine whether the sampling method is independent or dependent. A researcher wants to know whether the price of a one-night stay at Holiday Inn Express is less than the price of a one-night stay at a Red Roof Inn. She randomly selects 8 towns where the location of the hotels is close to each other and determines the price of a one-night stay. So of course it's bolded already, but we want to recognize that the 8 towns that were selected have an influence on the hotels that are selected, because the location of the hotels needs to be close to each other in order for us to compare. That is, the sampling method is dependent since each of the Holiday Inn Express hotels can be matched with one of the Red Roof Inn hotels according to town. That is, referring to the definition, the individuals selected in the first sample are used to determine the individuals to be selected in the second sample. So when we select the Holiday Inn Express, we're also going to select a Red Roof Inn based on a similar location. Heading over to part B then, we're told a researcher wants to know whether the state quarters have a mean weight that is different from traditional quarters. He randomly selects 18 state quarters and 16 traditional quarters and compares the mean weights of the samples. Now, since he randomly selects 18 state quarters and 16 traditional quarters, but there's no mention of a connection between them, that allows us to know that the sampling method is independent. That is, the sampling method is independent since the state quarters that were sampled had no bearing on which traditional quarters were sampled. Also take note that we're comparing the means to each other rather than a direct comparison of one quarter to another, meaning we're comparing a group to a group as opposed to the previous example where we were comparing one hotel to a matched hotel based on location. And that's the key aspect when trying to determine matched pairs data, which is dependent or independent sampling like we see in this example. That's going to take us into our next objective where we discuss hypothesis testing regarding 2 population proportions from independent samples. So we're still thinking in terms of independent samples, but now we're going to discuss 2 population proportions. Similar to when we have hypothesis testing with one population, we've got some requirements to confirm before we can conduct the hypothesis test. Notice we're going to call the 2 populations P1 and P2, and our first requirement would be that the samples are independently obtained using a simple random sampling. Next is we have to have NP times 1 minus P to be greater than or equal to 10, but this needs to happen with each sample. So we see N1 times P hat sub 1 times 1 minus P hat sub 1 needs to be greater than or equal to 10, and the same needs to go with the second sample, that would be N sub 2 P hat sub 2 times 1 minus R P hat sub 2. And this will make sure that we've got a normal distribution for each population. And finally, each sample size is no more than 5% of the population size. We've seen this requirement again, but now it applies to each sample, not just the overall. One more new concept for us would be a pooled estimate of P, and that's given by P hat. Notice there's no subscript here. It's P hat where we pool our information together. We take the sum of x1 and x2 and divide that by the sum of n1 and n2. Heading into our steps to conduct the hypothesis test. Similar to our one population hypothesis testing, we first need to determine the null and alternative hypotheses. Now, as opposed to a single population where we're comparing P to a number, notice that we're comparing P1 to P2 now. So we've got P1 is equal to P2 as our null hypothesis, and that applies to two-tailed, left-tailed, and right-tailed. But our alternative hypotheses compare P1 to P2, where we've got not equal to, less than, or greater than, based on the type of test we're conducting. As a quick side note, another way we could write this would be P1 minus P2 equal to 0. Think of this logically. If the null hypothesis is that P1 is equal to P2, we're saying that P1 is the same as P2. Well, simply another way to say that would be the difference between P1 and P2 is 0, because if there's no difference, then that means the 2 values must be the same, and sometimes we see it written this way, as opposed to setting the 2 proportions equal to each other. After our null and alternative hypotheses, though, we select the level of alpha, and that's typically given to us in the problem. And then our third step would be to calculate the test statistic, which would be z0. Notice that our formula gets a little bit larger now since we're incorporating 2 different samples. And make sure we're extra careful to note that this is a p hat in the denominator that represents our pooled estimate as previously discussed. So altogether we have p hat 1, p hat 2, and also our pooled estimate that is just p hat. Continuing to our next step then, we would need to find the corresponding p-value, and notice we're back to the normal CDF function. We've got a normal distribution when we're working with these proportions, so we're using the normal CDF function. Remember, with a two-tailed test, we have to be careful to double the area under one of those tails if we find only one of them. And after we have our p-value, we can state our conclusion, that if the p-value is less than alpha, just like we've seen before, we get to reject the null hypothesis. Heading into our first example then, we're told an economist believes that the percentage of urban households with internet access is greater than the percentage of rural households with internet access. He obtains a random sample of 800 urban households and finds that 338 of them have internet access. He then obtains a random sample of 750 rural households and finds that 292 of them have internet access. We're asked to test the economist's claim at the alpha equals a 0.05 level of significance. Well, since we're conducting a hypothesis test, we know we need to check for the requirements to conduct the test first. However, before we even do that, a big thing with these two population tests is simply organizing all our information. So first, I'm going to call the urban households our sample number 1. And of course, that means our rural households will be our sample number 2. That means the 800 urban households that were sampled represent our N1, and the 338 of them that had internet access would represent our X1. Similarly, our 750 rural households that were sampled represent our N2, and the 292 of them that had internet access represent our X2. We also want to make sure we're careful to note that the claim is the urban households with internet access is a greater percentage than the percentage of rural households with internet access. Taking that to our requirements then, first the samples are simple random samples that were obtained independently. Next, I have the information filled out for us already, but N1 p hat 1 times a 1 minus p hat 1 ends up being greater than or equal to 10, and N2 p hat 2 times 1 minus p hat 2 is also greater than or equal to 10, which means we can assume the sample proportions will be normally distributed. And finally, each sample size is less than 5% of the population, keeping in mind the populations would be the total amount of urban households, and then the other population would be the total amount of rural households. And we know there are a ton of them out there, so we're all set with our requirements. Heading into our hypothesis test setup then, we've got two population proportions we're comparing, so the null hypothesis would be that P1 is equal to P2, and remember the claim is that urban is greater than rural, and we call the urban sample our sample number 1, and rural our sample number 2, so the alternative hypothesis is P1 greater than P2. We just have to be careful with how we organize this. Remember, this can also be written as our null hypothesis being P1 minus P2 is equal to 0 versus the alternative hypothesis of P1 minus P2 greater than 0. And like we've seen plenty of times, the level of significance coming from the problem would be alpha equal to a 0.05. That means we're ready to calculate the test statistic, that is z naught, and we show the values of p hat 1 and p hat 2 in the requirements already, but we'll go ahead and calculate those first to make sure we're all comfortable with it. That is, p hat sub 1 is equal to an x sub 1 over an n sub 1, and that's equal to a 338 over 800 to give us a p hat 1 of approximately 0.4225. And our p hat 2 is equal to an x2 over an n2, which would be equal to our 292 over 750, giving us a p hat of approximately 0.3893. Now remember, the other piece we need would be p hat that is the pooled estimate, and the sum of x1 and x2 is divided by the sum of our sample sizes. So our p hat would be a 338 plus 292 divided by the sum of 800 and 750, and we end up with a pooled estimate of approximately 0.4065. Which means we can take each of our key values and substitute them into the formula for our test statistic, or p hat 1 was our 0.4225, p hat 2 was our 0.3893, and p hat is our 0.4065. Remember, n sub 1 is 800 coming from our first sample, and n sub 2 would be 750 coming from our second sample. Carefully putting this into our calculator, we end up with our test statistic, that is z naught approximately 1.33. And now that we have our test statistic, we can find our p-value using the normal CDF function, remembering first to draw our curve, and we've got a normal distribution with a test statistic of 1.33, and we're trying to find the area to the right of that test statistic since we have the claim that urban is greater than our rural. So that means our p-value is equal to the probability that z is greater than or equal to our 1.33, which means we're using the normal CDF function again from 1.33 up to our 10 to the 99 since we're finding the area to the right of our z statistic, and we end up with a p-value of approximately 0.0918. As we've done before, comparing that to our alpha level of a 0.05, our p-value is greater than alpha. Therefore, we do not reject our null hypothesis. And that means our conclusion is there is insufficient evidence to conclude that the percentage of urban households with internet access is greater than the percentage of rural households with internet access. And we're all set with our hypothesis test. That takes us to our next objective then, where we need to construct and interpret confidence intervals for the difference between two population proportions. First, introducing our requirements. Hopefully these seem familiar. We need our samples to be independently obtained using simple random sampling. We also need NP1 minus P to be greater than or equal to 10 for each individual sample, and then each sample size needs to be no more than 5% of the population size. Continuing on to the part that usually makes students feel a little more excited, sarcastically speaking that is, we have our bounds to construct these confidence intervals for population proportions, which means we now have p hat plus or minus our margin of error, where p hat in this formula is found by taking p hat sub 1 minus p hat sub 2 from the individual samples that is. And then our margin of error is calculated by this beautiful chunk of math, incorporating p hat 1 and p hat 2 along with our individual sample sizes. And notice that we're still using z sub alpha over 2, similar to when we've constructed a confidence interval for a single population. Of course, we need to know this by hand in preparation for free response questions on an exam. Heading into our example then, we're reverting back to the previous example where an economist obtained a random sample of 800 urban households and finds that 338 of them have internet access. He obtained a random sample of 750 rural households and found that 292 of them had internet access. But this time, as opposed to conducting a hypothesis test, we're asked to construct and interpret a 99% confidence interval for the difference between the proportion of urban households that have internet access and the proportion of rural households that have internet access. Organizing our data again, remember we have 800 urban households, and we're going to call that N1, and that makes our 338 of them our X1. The 750 rural households was our N2, and the 292 of them who had internet access is our X2. Now before we construct the confidence interval, we know that we need to check our requirements, but since we're just referring to the previous example, we're going to go ahead and recognize that we've already verified the requirements when we conducted the hypothesis test. And let's jump straight into the math. First, starting out with what we found previously, we had a p hat 1 from our hypothesis test that we found as 0.4225. And repeated in our problem, our sample size for sample 1, the urban households, is N1 equal to an 800. We previously found p hat 2 to be a 0.3893, and our sample size N2 is a 750. Now remember the bounds of our confidence interval would be p hat plus or minus our margin of error E, and of course that means we need our beautiful formula in order to construct our lower and upper bounds. Well, if we start off by substituting the values that we already have, we have our beautiful long formula with almost everything already found, and we just need to find z sub alpha over 2 again like we've done in the past. Well, remember to find z sub alpha over 2, we first need to recognize alpha, which is the complement of our confidence level, so 1 minus our 0.99 gives us a 0.01, and of course that means alpha over 2 would be a 0.005. And that means to find z sub alpha over 2, we're finding z sub a 0.005, and that means we're doing an inverse norm of a 1 minus our 0.005. And that means we end up with a z sub alpha over 2 value of approximately 2.58. Substituting that into our formula for our lower and upper bounds, we've got all the values that we need, and we can go ahead and find those values of the lower and upper bounds. Inputting our formula carefully into our calculator, we end up with a confidence interval with a lower bound of a negative 0.0311 and an upper bound of 0.0974. That is, we are 99% confident that the difference between the proportion of urban households that have internet access and the proportion of rural households that have internet access is between negative 0.0311 and 0.0974. Now we want to be able to connect the confidence interval to our hypothesis test here. And the big idea is, since the confidence interval contains 0, we are unable to conclude that the proportion of urban households with internet access is greater than the proportion of rural households with internet access. Going a bit more visually, constructing our confidence interval, our lower bound is negative 0.0311. Our upper bound is positive 0.0974. And remember, since this is a 99% confidence interval, we are 99% confident that the true difference in the proportions is within our lower and upper bound. And that means, since 0 is in that interval, it's possible that the true difference is 0. And that means we're unable to conclude that the proportion of urban households with internet access is greater than the proportion of rural households with internet access. And before we wrap up the discussion, we can check our hypothesis test results and confidence intervals using our calculators. That is, we have programs to do each of these. Still using the urban and rural data that we've been working with. First, we'll walk through a hypothesis test. As you see on our notes, we can find the p-value of our hypothesis test using the 2prop_z test function on our calculator. Connecting it logically, we've used a 1prop_z test function before. Now it's a 2prop_z test because we've got two populations and we're testing proportions. Remember, the z refers to a normal distribution, which means we've checked to make sure our requirements have been met. Heading over to our calculator then, like we see in the notes, we're going to hit stat and then tests, and we're looking for the 2prop_z test function, which would be our option number 6 on my screen. Hitting enter to enter the test, we have our x1 value of our 338, which comes from our first sample, and the sample size was at 800. Remember, that was our urban households. Our x2 is a 292 with an n2 of 750 from our second sample. And our hypothesis stated that our urban was greater than our rural, so we've got P1 greater than our P2. Hitting enter on calculate, we get the results of the test. And hopefully feeling familiar, P represents our p-value. Notice they give us p-hat1, p-hat2, and also p-hat, which is our pooled estimate. That is, our calculator functions gives us about everything we needed in our formula, so we can confirm our math if we did this on a free response question on the exam. Heading back to the notes then, just confirming one more time, we found our p-value to be a 0.0920. Remember, when we did it by hand, we found a 0.0918. And those are just slightly off from a little bit of rounding error. Heading over to the confidence interval then, still using the same data. Remember, we were asked to construct a 99% confidence interval for the difference in the proportions. So in our calculator, we're going to use the 2prop_z int function now. Heading over to our calculator one more time, like you see in the notes, we're going to hit stat, we're going to hit test again, and we're looking for the 2prop_z int function. I'm going to hit the up arrow to skip down to the bottom, and notice option B is our 2prop_z int function. Hitting enter on the function, we still have our x1, n1, x2, and n2 values in since we just did the 2prop_z test and those are connected. Our C level is the confidence level, so we need to change that to a 0.99 and we can calculate. Hitting enter on calculate, our calculator gives us our confidence interval, our lower bound of a negative 0.311 and our upper bound of a 0.0974. Notice again they give us p-hat1 and p-hat2, so again the calculator function gives us the values we needed for our formula, with the exception of our z sub alpha over 2. Heading back over to the notes, just tying in our calculator to our results and interpretation like we stated previously. We found the difference in proportions to be between our negative 0.03 and our 0.10 if we just round to 2 decimal places. And we're all set with confidence intervals and hypotheses tests on our calculator for 2 population proportions. And thank you again for joining us.